Okay, let's dive in. We've all seen what these large language models can do, haven't we? I mean, they tackle complex problems, reason through stuff. It's pretty amazing. And a lot of that power, especially for getting them to really think step by step, that comes from reinforcement learning, RL.
That's right. Yeah, RL fine-tuning is it's how models kind of learn to adjust what they're doing based on feedback. They basically learn by, well, trial and error to get better, more strategic on specific tasks. It's been huge for performance on, shorter text problems.
Right. Problems that fit in a, let's say, standard context window, a few thousand tokens, maybe.
Exactly, where the model can often lean on its internal knowledge base.
But, okay, here's the tricky part. The real world isn't just short bits of text, is it? You've got these huge documents, legal stuff, research papers, financial reports going back years, tons of information. So the big question, the real challenge is how do we get that same RL magic, that reasoning power, to work effectively when the model has to deal with like all of that at once?
Exactly, that's the frontier. And applying those standard RL methods that work so well for short contexts, well, they really hit roadblocks when you scale up. The research calls it a critical unsolved challenge because you see the core issue changes. For long context reasoning, the model can't just rely on what it already knows. It absolutely has to actively go out, find, and ground its reasoning in the information within that massive input.
Ah, okay. So it's not just more words. It's a fundamentally different task. Searching, retrieving, using that external text.
Precisely. And that's where standard RL starts to struggle a lot.
So what makes it so hard? What are the specific technical hurdles the research points out?
Well, they identify a few key things. First, there's suboptimal training efficiency. Basically, you see this delayed reward convergence. It just takes way, way longer for the model to start showing improvement during training compared to short context tasks.
It learns incredibly slowly, like it's wading through treacle.
Yeah, exactly. It's like it's lost in this giant library and takes forever just to figure out how to find the right book, let alone read it. And related to that, you get reduced output entropy,
Entropy, meaning the variety of its responses.
right? There's a marked reduction. The model's outputs become much less diverse during training. It tends to repeat similar approaches. And that restricts exploratory behavior, which is really bad because exploration is exactly what you need to solve complex problems hidden in long texts.
So just when it needs to explore this huge space, its ability to actually do that exploration shrinks. That sounds counterproductive.
It absolutely is. And it leads to the third problem, an unstable optimization process. You see these intermittent spikes in KL divergence. Now, KL divergence, simply put, measures how much the model's strategy changes during training updates.
Okay.
Big spikes mean the changes are erratic, unstable. It's hard to get consistent improvement when the training is jumping all over the place.
So it's slow, it gets stuck in ruts, and it's unstable. Anything else?
One more big one, variance amplification. Because you're dealing with long documents of varying lengths and the answers themselves can be long and complex, you have this heterogeneous input length distribution. This variability in the data leads to greater variability during policy updating. It adds a lot of noise to the training signal, making it even harder to control the learning process.
Okay, so slow, repetitive, unstable, and noisy. Yeah, I can see why that's a critical unsolved challenge. It sounds incredibly frustrating to work with.
It really is, and it's what limits using these powerful models for things like, deep research synthesis or analyzing complex legal cases. It's a major bottleneck.
Right. So this deep dive is focused on QwenLong-L1, which is presented as a solution. How does this framework actually try to overcome these specific thorny technical problems? What's the core innovation?
QwenLong-L1 is positioned as the first RL framework designed specifically for long context LRMs. And its central strategy, the really innovative academic idea here, is what they call progressive context scaling.
Progressive context scaling? Okay, like gradually increasing the weight you're lifting.
That's a good analogy. Instead of throwing the model into the deep end with, say, 100,000 tokens right away, you structure the training to gradually increase the context length, the difficulty it has to handle.
Makes sense. How is that implemented? What are the components of this framework?
It's built around three main technical components working together. First, they start with warm-up supervised fine-tuning, XFT.
Okay, SFT isn't new, but the warm-up part sounds specific here. What's its role?
Its purpose is very specific in this framework, to establish a robust initial policy. It's about deliberately building the model's fundamental capabilities, understanding context, generating reasoning steps, extracting answers, before you subject it to the potential chaos of long context RL.
So teach it the basics on more manageable text first. Build a good foundation.
Precisely. They use high-quality demonstrations from a teacher LRM, focusing on examples within an initial shorter context length, L1, which they set at 20,000 tokens. And the ablation studies show this is really important. This warm-up SFT accelerates reward improvements later on and helps keep the training smoother. They mentioned a lower gradient norm. It gives that robust and efficient initialization.
Got it. SFT provides a stable starting point. Then how does the progressive part actually happen?
That's the second and arguably the core component. Curriculum-guided phase RL, this is where the progressive scaling really comes into play, and it's designed to stabilize short to long context optimization.
A curriculum, like for school.
You can think of it that way. Instead of one giant RL phase, they break it down into K discrete phases. And crucially, in each phase, they progressively increase the target context length. So phase 1 might only use examples up to, say, 20K tokens. Phase 2 might go up to 60K tokens, and so on.
Oh, I see. So you're not making the huge leap from short to very long contexts all at once. You build up the capability step by step.
Exactly. And this phased approach is shown to bring substantial performance improvements and directly combats that inevitability we talked about. They contrast it sharply with single-stage RL, which they show leads to heightened instability, those fluctuating KL divergence numbers, and entropy collapse. This curriculum design is technically fundamental to stable adaptation.
Okay, that makes a lot of sense. SFT for the base, phased RL for stable scaling. What's the third piece?
The third innovative element is difficulty-aware retrospective sampling.
Retrospective sampling, looking back at past examples.
Yes, but specifically looking back at the hard ones. The goal here is to prioritize exploration of complex instances and really incentivize the policy exploration that gets dampened in standard long context RL.
So it doesn't just train on the current phase's data, it revisits difficult examples from earlier. How does it know what's difficult?
They use a clever mechanism, important sampling weighted by difficulty scores. They figure out the difficulty score for an example by looking at the inverse mean reward, the base model achieved on it previously.
Inverse mean reward. So low reward means high difficulty.
Exactly. If the model consistently struggled with an example, got low reward, it's marked as difficult. The framework then prioritizes resampling these hard cases from past phases during later training stages, and the impact it yields further performance enhancements. By forcing the model to revisit and grapple with these tough cases, it drives exploration. They observe higher policy entropy, pushing the model to find better solutions for the really challenging parts of the task.
Right, so it prevents the model from just getting good at the easy stuff and ignoring the hard parts. That's smart. SFT base, phased scaling, difficulty sampling focus. Quite a comprehensive approach.
It is, and they also mention one other technical detail as part of the framework: hybrid reward mechanisms.
Ah, yes. Evaluating answers in long context tasks must be tricky. It's not always a simple yes, no, or a single number.
Precisely. You need to balance precision and recall. So they combine two methods. First, rule-based verification, strict checks for formats, keywords, etc. But they combine that with an LLM as a judge. They use a smaller, reliable model like Qwen2.5-1.5B-instruct to assess semantic equivalence. Does the answer mean the same thing even if it's worded differently?
Okay, that sounds much more robust for complex answers.
Yeah, and the final reward signal for the RL is the maximum score from either the rule-based check or the LLM judge. This gives a richer, more accurate feedback signal.
All right, so that's the QwenLong-L1 framework, SFT warm-up, phased RL curriculum, difficulty sampling, and hybrid rewards. A lot of innovative technical ideas packed in there. How did it actually perform?
They put it to its paces on 7 standard long context document question answering benchmarks. These cover diverse reasoning types: mathematical, logical, multi-hop, using benchmarks like DocMath, Hotpot QA, Narrative QA.
And the results. Did the framework deliver?
The paper reports superior performance. Looking at their results, the QwenLong-L1 model, their larger one, performs on par with leading proprietary LRMs like Claude 3.7 Stylet Thinking.
Wow, matching Claude 3.7 Sonnet is definitely impressive, especially for an openly described research framework.
It is significant, and it significantly outperforms other strong models mentioned, including OpenAI-o3-mini and Qwen3-235B-A22B. Even their smaller 14B parameter version, QwenLong-L1 14B, performs very well, showing superior performance over Gemini 2.0 Flash Thinking and Qwen3-32B.
So the framework really pushes performance, but how much of that boost comes specifically from the complex RL part compared to just doing the SFT warm-up? That seems like a key academic question.
Absolutely, and they provide clear data on that. The results show significant gains specifically from the RL training enabled by this framework. The numbers are pretty stark. The 14B models gained an average of 4.0 to 4.1 points from the full RL framework over just the base model. The 32B models gained even more, 4.7 to 5.1 points.
That's a really substantial jump just from the RL component.
It is, and you contrast that with the limited efficacy of SFT alone. Doing only the SFT warm-up gave some improvement, sure, 0.8 points for the 14B, 3.2 for the 32B, but it's far less from the gains from the full RL process. It really highlights that while SFT provides a necessary foundation, the carefully designed RL phase is indispensable for reaching top-tier performance in these long context tasks.
That's a critical insight for developers, isn't it? SFT gets you partway there, maybe efficiently, but you need RL and likely this kind of structured RL to really excel.
Precisely, and the research offers more insights beyond just the scores. They look at why the framework works. Going back to the progressive context scaling, their analysis confirms it directly addresses those earlier challenges. It promotes higher entropy, keeping exploration alive, and stabilizes KL divergence, preventing those erratic training jumps.
So the phased curriculum directly counters the instability and exploration collapse seen in naive long context RL.
Makes sense. What about the interplay between the SFT and RL? You said SFT alone wasn't enough, but is there more to it?
Yes, they delve into the SFT versus RL trade-off, which is another key academic contribution here. They acknowledge SFT is an economical way for performance enhancement. If you need acceptable performance with less compute, less complex infrastructure, maybe less RL expertise, SFT is a good route. Okay, the practical choice for getting decent results more easily.
Right. But again, RL is indispensable for attaining optimal results. And here's the perhaps counterintuitive finding. They argue that maximizing performance necessitates prioritizing RL over SFT in terms of the overall training budget or effort.
Prioritizing RL over SFT, I would have thought more SFT just gives RL a better head start. Why would you prioritize RL?
Because their analysis suggests excessive focus on SFT risks trapping models in local optima.
Ah, okay.
If you overtrain with SFT, the model learns the patterns in those demonstration examples too well, too rigidly. It gets stuck in that specific way of solving problems. Then, when you apply RL, which needs to explore beyond those initial patterns to find truly better, more general strategies, the model struggles to break free from that SFT-induced local optimum.
So too much SFT can actually hamstring the RL phase later on. That's fascinating. You need SFT for the basics, but the real performance gains require letting RL explore more freely.
Exactly. It's a delicate balance, but the message is clear. Don't overdo the SFT if you're aiming for peak performance via RL.
What else did they observe happening during the RL training? Did the models just get better scores, or did their behavior change?
That's another really interesting part, the emergence of reasoning behaviors. They identified 4 key behaviors that seem to develop and strengthen during the QwenLong-L1 RL training: grounding, sub-goal setting, backtracking, and verification.
Okay, those sound like steps humans might take. Grounding is finding the relevant facts in the text.
Yes, pulling out and using the right pieces of information from the long context. Sub-goal setting is breaking the main problem down. Backtracking is recognizing an error in its reasoning and correcting course. And verification is double-checking its work, intermediate steps, or the final answer.
And these behaviors actually increase during the RL training.
Yes, they increase progressively during RL training, and, importantly, this increase correlates with performance gains. The model isn't just stumbling onto right answers more often. It seems to be developing a more structured, robust internal process.
What about the SFT-only models? Did they show these behaviors too?
They did show increases in these behaviors after SFT training, but, and this is a crucial distinction they make, despite SFT leading to significantly increased reasoning behaviors, these efforts fail to improve the final performance.
Whoa, hold on. So SFT makes the model try to do things like grounding and backtracking more often, but it doesn't actually get better at solving the problem.
That seems to be the implication. SFT teaches the model to perhaps exhibit the surface characteristics of these behaviors, maybe because they were present in the demonstration data. But it's the RL training within this framework that teaches the model how to use these behaviors effectively and in coordination to actually navigate the complexity and arrive at the correct answer.
So RL teaches not just the presence of the behavior, but its functional application for problem solving. That's a really powerful insight into what RL is achieving here beyond just score optimization.
Exactly. It suggests RL is fostering a more genuine cognitive capability, not just mimicry.
The case studies probably make this clear.
They do. Take case Complong Testimony 183. It involves calculating a capital cost from a dense financial document and needs careful reading and calculation.
Okay, a realistic challenge.
The base model, just the raw distilled model, gets confused. It's misled by the irrelevant temporal of financial information, botches the interest calculation, gets the wrong number, $20.04 instead of $32.04.
Lost in the details. Happens to the best of us. What about the SFT model?
The SFT model, even after its training, still fails to resolve this issue. The paper describes it showing persistent limitations, getting stuck overanalyzing unrelated documents, showing uncertainty and self-doubting behavior. It even runs out of tokens without an answer.
So it tries, maybe it even shows more grounding by pulling up lots of text, but it can't synthesize or correct itself effectively.
That's the picture painted. It lacks effective backtracking and verification to filter the noise or fix its path. Now compare that to the QwenLong-L1 14B model, the one trained with the full framework. It also initially exhibits similar distractions, makes some early mistakes, but crucially, it then quickly engages in effective self-reflection. It uses timely verification and backtracking to identify the errors, filter out the irrelevant details, and ultimately arrives at the correct $32.04 memers.
So it doesn't just get distracted, it recovers from distraction using the behaviors learned through RL. That really highlights the difference.
Precisely. It demonstrates a more robust reasoning process capable of self-correction in a complex environment. QwenLong-L1 265 involving interest calculation after a loan extension further illustrates this. QwenLong-L1 navigates the details correctly.
And these cases show the behaviors in action.
Yes, the authors use them to show how grounding, sub-goal setting, backtracking, and verification emerge and interplay in practice within the RL-trained model. It provides evidence for the development of these internal cognitive behaviors fostered by the framework.
Okay, this is really compelling stuff. It's not just about longer context windows, but about enabling more robust, human-like reasoning within them. Where does this research point next? What's the future work?
They suggest a few exciting directions. First, scaling real-world tasks. Taking this beyond benchmarks to truly complex domains like automated scientific research. Imagine an AI reading and synthesizing entire fields of literature or analyzing long videos.
Applying this kind of deep reasoning to massive, messy, real-world data?
Second, developing advanced architectures. Continuing to improve the underlying tech like more optimized attention mechanisms, they mention linear and sparse attention, and building efficient infrastructures to handle these huge models in context better.
Making the engines faster and more capable. Standard, but important.
And third, a direction that sounds particularly fundamental from an academic perspective. Rethinking long context RL paradigms. They propose exploring a shift from making decision at the token level to a turn-level Markov decision process, MDP.
Turn-level MDP, how is that different?
So instead of the RL agent deciding essentially which word to generate next, token level, it would operate at a higher level. A turn might involve deciding to read a specific section, or query a knowledge base, or attempt to synthesize an answer based on current information, or verify a previous step.
So the RL is guiding the overall process of interacting with the long context, not just generating the output word by word.
Exactly. It's breaking the huge problem down into a sequence of higher-level actions or interactions, and the potential payoff they mention is huge. They suggest this might enable the breakdown of long context into sequential interactions, optimizing them iteratively, potentially leading towards infinite context RL systems.
Infinite context, that phrase again. Systems not bound by a predefined context length. That's quite a prospect.
It really is. Imagine models that could genuinely reason over practically limitless streams of information.
Okay, let's try to summarize this deep dive. QwenLong-L1 offers a really innovative multi-part RL framework. It makes significant strides in making reinforcement learning stable and highly effective for large reasoning models working with very long documents. It tackles those core technical challenges, inefficiency, instability, lack of exploration head-on with smart techniques like the phrased curriculum and difficulty-aware sampling, achieving state-of-the-art results.
And the key insights for us, I think, are understanding why long context RL is so hard, seeing how tailored structured approaches like this can overcome those hurdles, and appreciating the crucial but potentially tricky relationship between SFT and RL.
Right, SFT for a good start, but prioritize RL for peak performance and don't overdo the SFT. Plus, the really fascinating insight that this kind of RL doesn't just boost scores, it genuinely seems to foster more effective internal problem-solving behaviors.
It's teaching the model how to think more robustly in these complex information environments, not just mimicking answers. The emergence of grounding, backtracking, verification, that's really significant.
So, for you listening, what this research signals is clear progress on a major AI limitation. We're moving towards models that can ingest and reason over much larger swaths of information, getting closer to handling the scale and complexity of real world knowledge.
And that opens up so many possibilities for science, research, analysis, areas currently bottlenecked by the sheer volume of information.
Absolutely. And let's end with that provocative thought the researchers themselves raised the potential for infinite context RL systems. Just take a moment to imagine that. Models that aren't constrained by how much they can read at once. What currently unsolvable problems reliant on synthesizing vast, disparate information could suddenly become tractable if AI could truly reason across a virtually limitless context. What new scientific breakthroughs or creative insights might emerge, that's the kind of future this innovative academic research is paving the way towards.